Let's try to solve this problem here. The figure above shows a 0.300 kg object released from A. Okay, so you can see this object is placed at position A, and this object here has a mass of 0.300 kg. Then it's released from A. So if it's released from A, we can know that it starts at 0 meter per second. Okay, then it's released from A. What else? Move to C through B and stop at C. So it will move towards C, but it will pass through B in the middle of the journey, and it will stop at point C. If it stop at point C, you should expect once the block reach point C, you should have 0 meter per second over here. Okay, track AB is frictionless, so this portion of the journey should be frictionless. Then track BC is rough, so this portion of the journey you should expect some kinetic friction throughout the journey. Okay, so they ask for the speed of the object at B, the work done by frictional force, the coefficient of kinetic friction, various stuff. Okay, so again here we'll be using principle of conservation of energy, but over here there are actually two portions of journey. Let's spend some time to figure out which portion of the journey can use principle of conservation of mechanical energy, which portion of the journey we cannot use principle of conservation of mechanical energy. To do that, we will try to draw a free body diagram for the first portion of the journey and the second portion of the journey. Then we see whether it follows the criteria for principle of conservation of mechanical energy to be used. Let's draw the free body diagram for the block throughout this journey from A to B. And let's pick a one point on this journey from A to B to draw the free body diagram. Let's pick this point over here. Okay, somewhere in the middle between A and B. So if you draw a free body diagram using a dot to represent the object, then you have an axis. This is the one that is parallel to the slope. This one is one that is perpendicular. Okay, so this will be your axis. Then you should expect the object to have weight because it has mass. Then you should expect a normal force pointing perpendicular to the slope, to the inclined plane or the plane over here. Okay, because normal force is always perpendicular to the surface you are touching. So I believe that's all the forces that are acting on this object over here. Since track AB here is frictionless, so you should not expect there's any kinetic friction happening in this free body diagram. So this is the journey from A to B. Next, we look at the journey from B to C. For the journey from B to C, again you use a dot to represent the object of interest, which is your block. Then you have your axis perpendicular to the journey from B to C. Okay, so again this object here, it has weight because it has mass. The next thing is you have normal force since you are touching the surface. Then of course the object is moving towards the right. It's a rough surface, so you should expect the kinetic friction to be pointing in the opposite direction, which is towards the left. Okay, so this is the free body diagram for the object while it is in motion from position B to position C. Okay, so let's try to determine whether the principle of conservation of mechanical energy can be used or not. For principle of conservation of mechanical energy to be used, you have to make sure that the total work done by the non-conservative force equals to 0. So the work done by non-conservative force should add up to be 0, or there should be no work done by non-conservative force. Okay, so the weight over here, it's a conservative force. The only two forces that are conservative in our syllabus for chapter 5, it's the work done by gravity and the work done by the restoring force of a spring. These two work done here are work done by conservative forces. The rest are non-conservative. So the normal force here is non-conservative. Kinetic friction here is non-conservative. Non-conservative for normal force, conservative for the weight. Next, we try to look at where is the object, which direction is the object moving. So at this journey from A to B here, the object is moving in this direction. And for object from B to C, the object is moving in this direction. Okay, so now let's try to see whether the non-conservative force are contributing any work done or not. If they are contributing a work done, then the system will not be, the mechanical energy of the system will not be conserved. Okay, so for this non-conservative force in the first diagram, we have the normal force, the non-conservative force, but the normal force is perpendicular to the displacement here. And since they are perpendicular, theta will be 90 degree, cos 90 degree will be 0. So here, the non-conservative force, which is the normal force, is contributing no work done to the object over here. So for the journey from A to B, the only force that is doing work will be the weight, because the weight you can resolve it into two components. One component that is perpendicular to the displacement, and one component which is parallel to the displacement. So only the component that is parallel to the displacement will be doing work, and in this case, since the parallel component, the work done by weight parallel to the displacement, it's in the direction of the displacement. Therefore, you should expect a positive work done by gravity over here. And since the positive work done by gravity over here is the only force doing work, you should expect a positive total work done. And since it's a positive total work done for this journey over here, you should expect the speed of the object to increase, because positive total work done means positive change of kinetic energy. Positive change of kinetic energy means positive change of speed. Thus, it means speed up for the journey from A to B. Okay, you have to relate a bit to your work energy theorem. Okay, next for the journey from B to C, let's look at the non-conservative force, see whether it do any work or not. For the normal force over here, the normal force and the displacement are 90 degrees with each other, so you should expect the normal force to do no work in this case, 0. Okay, but there's another normal force for this journey from B to C, which is the kinetic friction. And unfortunately, the kinetic friction and the displacement are parallel with each other, just that they are in opposite direction. And if they are in opposite direction, the work done by kinetic friction will not be equal to 0. In fact, it will be a negative work done by kinetic friction. And since this is the only force doing work on the object right now, your weight will not be doing work because it's perpendicular as well. So since kinetic friction is the only force doing work on the object, and the work done by kinetic friction will be negative since it's opposite the direction of displacement, thus the total work done for the journey from B to C will be negative. If the total work done is negative for the journey from B to C, you should expect the change of kinetic energy to be negative for the journey from B to C. And since the change in kinetic energy is negative for the journey from B to C, you should expect the speed to experience a negative change or decrease. The speed will decrease for the journey from B to C. So the journey from A to B will see an increase in speed, whereas the journey from B to C will see a decrease of speed until it comes to a stop at point C. Okay, so to make a conclusion, AB here, the mechanical energy is conserved, but from B to C, the mechanical energy is not conserved. Okay, so we will be using the principle of conservation of mechanical energy for the journey from A to B, but we will be using the general principle conservation of energy, not mechanical energy, just conservation of energy for the journey from B to C. Okay, so let's try to solve the problem. For question A, they ask for the speed of the object at point B. So we are interested in something about point B. We know most of the stuff for point A. So let's compare the mechanical energy for position A and position B by saying that the mechanical energy at position A is equals to the mechanical energy at position B. And mechanical energy is just the sum of the kinetic energy and gravitational potential energy at position A equals to the kinetic energy plus the gravitational potential energy at position B. There's no elastic material here, so I'm eliminating the elastic potential energy straight away. Okay, so this will be half mVA squared to represent the kinetic energy at point A, and you have a mg height at A for your gravitational potential energy at point A. Then you have half mvb squared for your kinetic energy at point B. You have your mg height at point B for your gravitational potential energy at point B. Now it's just a matter of substitution. Again, before I substitute, let's try to be clear where are we setting for our reference position. We'll be setting this ground here as our reference position. Okay, reference position is important when you're calculating the gravitational potential energy. So this is the position where we set h to be 0, thus the ug will be equals to 0. Okay, so substitution, half 0.300. The speed at point A will be 0 because the object is released at point A, so it should start at rest. Then 0.300, acceleration due to gravity will be 9.81, and the height at point A should be 1 meter. Equals to half 0.300. You're interested with the speed at point B, so leave it as it is, plus mgh. Your mass is 0.300. Your acceleration due to gravity is 9.81. Your height at point B, your point B is already at the ground already, so it's at the same height with our reference position. So our height will be 0. Okay, so over here what happens is this first term, the kinetic energy, and the last term, the potential energy, both will become to 0. So you are left with the mgh at position A equals to the kinetic energy at position B. So the only unknown left here is the speed at point B. So you can just use your calculator to calculate everything. And I believe you should get the answer to be the speed at point B equals to 4.43 meter per second. Okay, still doable, I believe. Next, let's look at the second question. Question 2 asks to determine the work done by frictional force. Well, the work done by frictional force can be, you can think of different ways to calculate it. First is by finding the magnitude of the kinetic friction, the magnitude of the displacement, and the angle between the vector of the kinetic friction and the displacement, which is 180. But if you use this method, right, you have the magnitude for displacement, yes. You have the angle between the two vectors, yes, it's 180. But you can't find the magnitude for the kinetic friction. Because to find the magnitude for the kinetic friction, you have to know your coefficient of kinetic friction, and you have to know the normal force, the magnitude of the normal force. You can determine the magnitude of the normal force by doing first law, Newton's first law for the y that I mentioned here, to determine your magnitude of normal force. But the issue is you can't have your coefficient of kinetic friction, because that's what you need to find for question 3. So in that case, because you don't have mu k, therefore you cannot determine the magnitude of kinetic friction. So we have to let go of this approach. We cannot use this straightaway approach to determine the work done by frictional force. Again, we can't determine work done by frictional force by multiplying the magnitude of kinetic friction, magnitude of displacement, and cosine angle between the two vectors. Because we can't determine the coefficient of kinetic friction, thus we can't determine the magnitude of kinetic friction. So what we can do is we'll take another approach, which is the work energy theorem approach. Because we know what will happen at the end of this journey, the speed of the object will be 0. And we also know the speed of the object at point B. So what will happen is we know the kinetic energy at point B and point C. So we know the change in kinetic energy for the journey from point B to point C. If we know the change in kinetic energy, we can relate to the total work done for the object while it is moving from point B to point C. And from there, we can try to determine the work done by frictional force. Okay, so let's take that approach. So the approach is work energy theorem. So you should expect work done total to be equals to the change of kinetic energy. And if you see work done total, what you need to do is you should draw a free body diagram to show what are the forces that are acting on an object. Because all the forces here will contribute different amount of work done, and if you sum them up, that will be your work done total. Okay, so let's do that. Work done total will be the work done by the normal force plus the work done by gravity plus the work done by the kinetic friction, and they will all equals to the change of kinetic energy. So you break down work total to the work done by each of the respective forces. Okay, you know work done by the normal force will be equal to 0 because the normal force is 90 degree compared to the displacement. Normal is here, displacement is here. The angle between them is 90 degree. So there should be 0 work done by the normal force. And what you left here is the work done by gravity and the work done by kinetic friction. And sum them up, you should get change of kinetic energy. Now, we know from the theory video that work done by gravity here is a work done by conservative force. So if it's a work done by conservative force, you can re-express the work done by conservative force in terms of the change of potential energy. So in this case over here, we can change this work done by gravity here to be the negative change of potential energy. In this case, gravitational potential energy. If you're not sure what I'm talking about, please refer back to the video where I try to explain why work done by gravity is equals to the negative change of gravitational potential energy. Okay, so you continue. This one is work done by kinetic friction, what you want to determine, and it's equals to the change in kinetic energy. So what you need to do now is you break open the delta, change it into final minus initial. So this is UG final. Let's do right final and initial. We know the journey is from B to C. So final should be point C minus initial. Initial should be point B. Okay. Then plus work done by kinetic friction equals to kinetic energy at point C minus kinetic energy at point B. Okay, until now it's still quite straightforward. What you do is you break open the delta to become final minus initial. This one you break it to become final minus initial. Okay, once you reach there, what you can do is you can rearrange. If you want to straight away substitute, it's okay as well. But let's rearrange it in a way that's more intuitive for everyone. So you keep all the position B terms on the left hand side. You keep all the position C terms on the right hand side. So we will bring the kinetic energy at point B to the left hand side. We will bring the potential energy at point C to the right hand side. So what will happen is you will be getting kinetic energy at point B plus the gravitational potential energy at point B plus the work done by kinetic friction is equals to the kinetic energy at point C plus the gravitational potential energy at point C. Okay, so what you have here is you have this side to be the mechanical energy at point B and this side to be the mechanical energy at point C. So mechanical energy at point B and mechanical energy at point C will be different. So the mechanical energy is not conserved. But the change in mechanical energy can be represented by the work done by kinetic friction. Because this work done of kinetic friction, the object experiences a change of mechanical energy from the initial mechanical energy to the final mechanical energy. The amount of change is equal to the work done by the kinetic friction. Okay, so this is the idea which we have mentioned in the video for principle of conservation of energy. Okay, so let's try to do our substitution. I'll rewrite the equation here. Kinetic energy at position B plus the gravitational potential energy at position B plus the work done by kinetic friction is equals to the kinetic energy at point C plus the gravitational potential energy at point C. Okay, again, this is the mechanical energy at point B, and after it experienced the work done by kinetic friction, the mechanical energy experiences a change, and the final mechanical energy will be the new mechanical energy, and it's different from the initial mechanical energy. Okay, So another way of writing it, I'll just write down, well, because I'm explaining also the theory, you can shift it, then it become work done by kinetic friction is equals to EC minus EB, right? So work done by kinetic friction is actually equivalent to the change in mechanical energy. Okay, so the work done by non-conservative force is equals to the change in mechanical energy. That's the idea. Okay, so let's move back to solve the problem. Substitute in the relevant formula for for kinetic energy and potential energy. So half mv squared plus mghb plus the work done by kinetic friction, leave it as it is. It should be half mv c squared plus mgh c. Now substitution, half mass of the ball is 0.300. At point B, your speed is 4.43. Okay, the answer is from here, 4.43. Oops. Square plus mgh height at point B to be 0 plus the work done by kinetic friction equals to half m vc. The speed at point C will be 0 because it reached a stop at the end of a journey, plus mgh 0.300, 9.81. The height will be 0 as well. Okay, so there's a lot of terms that will be equals to 0. Let's try to cancel it out first. This term here will become 0. This term here becomes 0. And this term here will become 0. So the only unknown left here is the work done by kinetic friction. So you can use your calculation to determine it. In essence, the work done by kinetic friction will be equal to the negative of the initial kinetic energy over here, because all the terms become 0 right now. Okay, so your work done by kinetic friction will be equals to negative 2.943 joule. Okay, so this will be your work done by kinetic friction. Okay, so now let's move on to the third question. Question 3 asks us to determine the coefficient of kinetic friction. So what we know about kinetic friction right now is the work done by kinetic friction is negative 2.943 joule. So I think because just now we mentioned that we cannot determine the work done by kinetic friction by multiplying the magnitude of kinetic friction with the magnitude of displacement with the cosine of the angle between the kinetic friction and the displacement. We said just now for question 2 that we cannot determine the work done by kinetic friction this way. But now we have determined the work done by kinetic friction using the work energy theorem. And well, this work done by kinetic friction here allow us to determine the magnitude of kinetic friction, because the magnitude of kinetic friction can be found by relating it to the work done by kinetic friction. Let's try to do that first. The work done by the kinetic friction is equal to the magnitude of kinetic friction multiplied by the magnitude of displacement multiplied by the cosine of the angle between the kinetic friction and the displacement. We do have the magnitude of the displacement. We do have the angle between the kinetic friction and the displacement. So we also have the work done by kinetic friction. So what we don't have here is just the magnitude of kinetic friction. So what we do now here will allow us to determine the magnitude of kinetic friction. Okay, so the work done by kinetic friction is negative 2.943 joule and equals to kinetic friction magnitude times 2 meter, which is the magnitude of the displacement, times cosine 180 degree, because these two vectors are opposite to each other. So if you do your calculation, you should get the magnitude of kinetic friction to be 1.47 Newton. Okay, now you have your kinetic friction, but what they ask for is the coefficient of kinetic friction. So you know that you end up need to use kinetic friction equals to the coefficient of kinetic friction multiplies by the normal force. So you need to find this. You already have this. So what you need to do now is you need to determine the normal force first. Then once you have your normal force and your magnitude of kinetic friction, you can do a calculation to find your coefficient of kinetic friction. So how do we find the normal force? We discussed earlier that we will determine the normal force by doing Newton's first law for your y dimension over here. So for the y dimension, the sum of force should be equal to 0 because the object never moves up or down. It remains at rest in the y dimension throughout the journey from B to C. It at rest, and it will still remain at rest throughout the whole journey from B to C in the y dimension. Okay, so for your y dimension, you can take your up minus down or down minus up, both are fine. So here it will be n minus the weight. I'll change weight to be mg just to avoid us confused whether it's work done or weight. Okay, so from here you know that the normal force will be equals to mg, and mg is just 0.3 times 9.81, so you get 2.943 Newton for your normal force. And now you have your kinetic friction 1.47, you have your mu k that you want to determine, you have your magnitude of normal force to be 2.943. Well, using your calculator, you should get the answer for mu k to be 0.5, and that will be the coefficient of kinetic friction. Okay, this question is quite an interesting question because it involves a lot of different concepts. First, it involves a principle of conservation of mechanical energy to determine the speed of the object at B. Then after that, to determine the work done by frictional force over here, you have to use the concept of principle of conservation of energy. To be more specific, you need to know that the work done by non-conservative force is equal to the change of mechanical energy of an object. Okay, then using that, you're able to determine the work done by frictional force. And when you proceed to question 3, you have to use back concept that you have learned from chapter 4. You use your Newton's first law to determine the normal force, and you use the equation for kinetic friction to determine the coefficient of kinetic friction. And that's how you will solve this problem over here.